Hey guys, welcome to week 2 of at-home learning. I hope week 1 went well. I know we had some device issues, but I hope you were able to access these videos, and I hope they were helpful to you. We're finally talking about exponential functions. Yay! We kind of talked about it a little bit when we talked about the geometric sequences. The geometric sequence formula, oh, by the way, I got a pen, so we'll have to see how this works, if y'all can read my handwriting a little bit better. But we talked about geometric sequences. And the formula for this was AN equals A1, so the first term, times R, the common ratio, to the n minus 1. That was the formula, but then we said that the equation above is in this form. It's in the form of y equals a times bx. And guess what? That is the exponential function. I know I dipped on it really briefly in geometric sequences. So a geometric sequence is an exponential function. It's something that's growing exponentially. So this part right here is what we're going to fill in to the formula. Y equals a times bx. So real quick, if we said it was a geometric, is it going to be linear? Well, no, because we said arithmetic was linear. It's growing at a constant rate. It's got a slope. It's got a constant rate of change. It's going up by the same each time. Exponential, it's something that's growing exponentially. I really like the example that was done in the last notes, the recursive sequences notes, and it gave you this example of a person, which kind of really fits in to our world today. One person gives off germs to 2 other people. Well, then this other person gives off germs to 2 other people this way. And this one does the same. And as you can see, it's growing exponentially. So now instead of 1, I've got 2, 2, I've got 4. And if we did it again, we'd have 8. So it's not growing at a constant rate. It's going up. It's multiplying by 2. We multiplied by 2 to get here and multiplied by 2 to get here. It's growing exponentially, not just going up in a linear equation with a slope. Okay, so back here. So this is a non-linear function. Non-linear function. It's not going to be a line. It's going to make some sort of curve. So if you look at our formula, the A is actually our y-intercept. The B this time is the common ratio. So it's kind of the same thing as R. It's just B in this formula because we can't keep anything simple in math, right? And then X is your exponent. In all exponential functions, you have X as the exponent. If you just have a number, it's not an exponential function. So keep in mind, for it to be exponential, the X is the exponent. And you've probably never seen that before. This is probably the first time to have the variable up in an exponent. So let's start simple. Let's do a little compare and contrast. It says, how are exponential functions different from lines? So it gave us an example of linear, so we know this one is going to make some sort of line on the graph. So if we look at x, to get from 0 to 1, well, we added 1. To get from 1 to 2, we added 1. To get from 2 to 3, we added 1. Now, if you look at y, To get from 2 to 4, we added 2. 4 to 6, we added 2. 6 to 8, we added 2. So just like we said, an arithmetic sequence adds or subtracts. It is a linear equation if it's arithmetic. So this lines, to make a line, you have to add / subtract. Add / subtract. Which again, this is an arithmetic sequence because you're adding. I guess taking the difference. If we look over here on the flip side, an exponential function, well, if I look at x's, again, I'm just adding 1. So far it looks the exact same as a linear. However, when I go over here, if I said I'm adding 4, well, to get to 8 to 16, I'm not adding 4, so that's not it. So what's another way to get here? Well, 4 times 2. 8 times 2 gives me 16. 16 times 2 gives me 32. So if you multiply or divide, and again, dividing is just multiplying by a fraction, multiply, it becomes exponential because it's growing exponentially. It's getting bigger faster, where a line, it's just going at a constant rate. If we were to see these on a graph, this would just be, well, at 0, we're up at 2. Whoops, okay. At 0, we're up at 2. At 1, we're up at 4. 3, 6, 4, 8. And it just makes a line. On the flip side, if we were to look at the graph of an exponential function, well, I start off at 0, I'm already at 4. 1, I'm shooting up to 8. 2 is shooting up to 16. And oh my goodness, 3 is way up here. So if you notice, this one is making a curve. There's a curve right here. It's not straight. It's not a line. Y'all, I think my handwriting's looking better. Okay. So if we go down here, do these tables represent linear or exponential graphs? Again, we're just going to look at the difference in the x values and the difference in the y values. So let's look at number first. Well, to get from 1 to 2, add 1. 2 to 3, add 1. 3 to 4, add 1. Now, what's happening here? Am I subtracting 4? Well, no, because 4 minus 4 would be 0, not 2, so that doesn't work. So this must be an exponential. I must be multiplying or dividing. Well, I went from big to small, so I know I'm dividing. And I know 8 divided by 2 gives me 4. 4 divided by 2 gives me 2. 2 divided by 2 gives me 1. That's supposed to be a 2, sorry. So since I'm multiplying or dividing, because of this, it is an exponential function. It's going to go at a faster rate, making a curve in the graph instead of just linear. So this is exponential. If I can spell. Good thing I'm not y'all's English teacher. Okay, let's look at number next. Again, if I look at the pattern here, if you notice, every time these are going to be what? That's right. We're going up by 1 most of the time. Okay. Because this is just the term in the graph. Now let's look at this side. How am I getting from 3 to 7? Well, add 4. 7 to 11. Oh, I can add 4 again. 11 to 15. Add 4. Well, I'm adding or subtracting, so that means it is arithmetic. Or it is linear. Multiply, divide, it's exponential. Add or subtract, it's arithmetic or linear. Let's look at 3. Again, -1 to 0, I'm adding 1. 0 to 1, adding 1. 1 to 2, adding 1. What happened here? Well, this I went and subtracted, it looks like. 12 minus 3 gives me 9. 9 minus 3 gives me 6, and 6 minus 3 gives me 3. So it looks like this one I'm adding or subtracting. In this case, I'm subtracting. So again, this is arithmetic, or in other words, it's linear. It makes a line. It's going up at a constant rate, or in this case, it's going down. It's going down 3 over 1, down 3 over 1. Ooh, decimals, yay. So again, this part's the easy part. I'm going up 1 each time. 1, up, 1. If I look on this side, it's not looking like I'm adding anything. Like if I added to get from 2 to 8, it would be 6. Am I adding 6 from here to here? Definitely not. So I'm betting I'm multiplying or dividing. And since I'm getting bigger from here to here, I know I'm probably multiplying. So since 2 and 8 are easy to figure out, I know 2 times 4 gives me 8. Well, what about 0.5 times 4? Well, hey, that gives me 2. And when I plug it in my calculator, this gives me 0.5. So I'm multiplying by 4, and since I'm multiplying, it's growing exponentially. It's getting bigger faster. It's not going at a constant slow rate. It is exponential. Exponential. So not too bad. You're just trying to find the common difference or the common ratio again. This one says, are these exponential functions? Here's the only thing you need to look at to figure out if it's an exponential function. Remember, like I said up here, this is the key, what I circled in red. It has to have an x in the exponent. If it's got any other number as an exponent, it's not exponential. X in the exponent makes it exponential. So if I look at 5, I've got an x in the exponent, so we're good. So this is, whoops. Exponential. If I look at 6, well, I look in the exponent, it's an x. So it's exponential. Last one. Oh, look at the exponent. It's a 3. Can I have a 3 for it to be an exponential function? No way, Jose. It's got to be an x, and there's not one there. So this is not exponential. Not exponential. Okay, moving on to evaluating these exponential functions for the given values of x. This is, remember my handy-dandy function machine I made that was so high-tech, and I plugged in a number and out came another number? There was some rule to my function. Well, it's giving you the rule and it's telling you to plug it in. So when it says f of 2, it really wants you to look at what they gave you, and everywhere you see an x, we're now going to plug in 2. That's what it's telling me. Everywhere I see an X, I'm plugging in a 2. So for f of 2 equals, I keep the 3 the same, keep the 5 the same. For the x, I'm plugging in that 2. So I have 3 times 5 to the second power, which is really 3 times 25. And 3 times 25 is 75, or you've got your handy-dandy calculator if you need it. If we look at 9, everywhere I see an X, this time I'm plugging in 7. Now it's not written in function notation, but it gives you what X is equal to. So that's how you're going to evaluate it. It's the same as the other, it just looks a little bit different. So to find Y, I do -6 times 1.8. Again, we're keeping this stuff the same, just bringing it down, but now instead of X, I'm supposed to plug in 7. Well, 1.8 to the 7th power is 61.22-ish. And then when you multiply that out, you should get -367.33. So not bad. Y'all have done this before. We talked about it at the very beginning of the year. Remember, this is just like my function machine. Okay, moving on. Going the wrong way. Sorry. Moving on this way. Okay, one definition, a new definition, is this. Asymptote. Yes, go ahead and laugh now. Asymptote. An asymptote is a line that the graph approaches but never intersects. So it gets super, super close to this line, but it's never, ever going to cross. And we're going to talk more about this in a little bit, but just keep that definition in mind because that's part of exponentials is the word asymptote. Okay. So graphs of exponentials. We've kind of looked at what graphs look like, and I showed you a little graph on the first page. So if A is positive, and if B is greater than 1, if your common ratio is greater than 1, and A is positive, you're going to have a graph that looks like this. So it's stretching out both ways, and it's getting closer to both axes. If A is positive, and if B is greater than 0 but less than 1, so it's some sort of fraction or decimal, half, 0.25, something like that, it's stretching out this way. That was a really bad arrow. A little bit better. It's stretching out this way, and again, it's approaching your X and Y axis. If it's negative and B is greater than 1, it's going to be flipped like this. And then if it is negative and it's a fraction or a decimal, it's flipped like this. So there's kind of a pattern with how they're going to look. So when you start graphing these, again, you can get a table of values super, super quickly on your calculator, which is what I would do because we're about to do this all by hand, and I would not do that. Again, I would do, I'll write the rule down below, but plug it into y equals and then hit second graph and look at the table, and you'll have all your points, and you just plot your points and graph, just like we did parabolas with quadratics. And again, I'll write that rule down here on the notes. So the graphs that have these characteristics, they're going to have these characteristics. So a graph is going to have a y-intercept, and that is going to be 0, comma, whatever a is, whatever this number is here. It's going to have a horizontal asymptote, which is going to be y equals 0. Well, anytime I have y equals anything, I know it's a horizontal line. And at 0, that's the x-axis. So the horizontal asymptote is the x-axis. Domain, remember, is Doller, left to right. Well, looking at these graphs, these arrows mean it goes on forever. So can I draw a line with how far left and how far right the graph goes? No, because they're going on forever. I can't do that. There's no way to do it. So the domain is negative infinity to positive infinity, or all real numbers, however you would like to write it. Now range is a little bit different. Range is the y. So that goes from bottom to top. Well, I have y equals 0 as the horizontal asymptote. So that's, it's never going to cross there. So y has got to be greater than 0 and less than infinity. So those are the characteristics. And again, these, if I can find the right button, these, horizontal asymptote, domain, range, is going to be the same for all. So let's try an example. So it gives us our equation right here. And it wants us to graph the function, identify the y-intercept and asymptotes of the graph, and describe the domain and range of the function. So again, this is how I would do it. Calculator way. Y equals, hit y equals on your calculator, plug 2 times 1 divided by 4, and then do the little caret button with an X, and then you're going to hit second graph. And then you can look at the list of tables, so we don't have to sit here and plug everything in for X into your calculator. I would do that. So for -1, we should get 8, 0 is 2, 1 is 0.5, 2 is 0.125, 3 is 0.03125, 4 is 0.0078125, and then 5, 0.019533125. Beautiful. So there's our points. Now to graph an exponential function, all you do is take these points and put them on the graph, just like you would linear or quadratic. Same things going on. So I think I'm going to count by 2s to give us some room. So we'll say this is 2, 4, 6, 8, 10, -2, -4. Now, I'm going to do -1, 8. So over -1, up 8 is the first dot. 0, 2 is the second point. So as you can see, there's a big difference already between the first couple. 1 and a half. So 1's about here, so a half is about right there. And then it's 2, 1.25, which is really close here. Really close. And they're just going to keep getting super close to the y-axis, but they are never, ever going to cross. So if you were to connect the dots here, it's getting super close, but your y-axis, here's the funny word again, ready? Asymptote. Your y-axis is your asymptote. It can never cross this line. It's going to get super, super, super close. It's never going to touch, ever. We could keep doing numbers. We could keep going down 6, 7, 8, all the way to infinity. We would never get to 0. They would just keep getting smaller and smaller here. Okay, so let's see what it's asking for. Y-intercept. So remember, that's just 0a, whatever your a is. Well, in this case, our a is 2. So it's 0, 2. Or you can look, well, to find y-intercept, you plug in 0 for x, solve for y. Well, this plugs in 0 for x, and y is 2. Either way. But if you just look at your equation, it's your a. The asymptote is y equals 0. It's going to get super close to that line, but it's never going to cross. Domain, I've got arrows going. It's going to go on for forever. It's going to get every x value there is. So it's negative infinity, positive infinity. And then range. Range is bottom to top. So again, it's never going to cross this line. It's never going below 0. So its bottom line would be 0. And I'm not including 0 because it's never going to be on 0. We talked about that. It's an asymptote. There's never going to be a point on the y-axis. The x-axis. And then it can go as far as it wants this way. It's going to keep going up forever. So that's to infinity and beyond. It's not too bad. Number next. So this time it gives us the graph, and we have to write the equation for it. So first thing, the equation again is y equals a times b to the x power, where we have a is our y-intercept. And b is the common ratio. Well, for a, the y-intercept, remember we talked about it on the last one. I can look at where I plug in x is 0 and get out what I get for y. So if I plug in 0 for x, I get out 3. So my y-intercept is 3. Whoops. Switch back here. Is 3 times, now this is the common ratio. Since it's exponential, I'm looking at my y's, and I want to see how am I getting from here to here. How am I getting from here to here? And it's exponential, so I'm multiplying or dividing. Well, 1.5 times 2 gives me 3. 3 times 2 gives me 6. 6 times 2 gives me 12. So I'm multiplying by 2. So my b is 2, and then the x stays there. So there's my equation. If we go to graph, let's do 1, 2, 3, 4, 5, and let's count by 3s. 3, 6, 9, 12, 15. If we go to graph, I'm just going to graph these points. So at negative 1, I'm at 1.5, so somewhere right there. 0, I'm at 3. 1, I'm at 6. 2, I'm at 12. 3, I'm way up here at 24. So as you can see, it's doing this. And if we were to check our equation with what it's supposed to look like, well, A is positive and B is greater than 1. So it should be looking like this. And that's what ours looks like. Y-intercept, again, we already kind of talked about that. That is 0, 3. Asymptote, y equals 0. It's going to get super, super close to this line. Never, ever going to cross. It's going to have so many little dots like right there. Never going to cross. Domain, negative infinity. Positive infinity. Again, these arrows indicate that it's going to keep going. In range, it's going from 0 and going all the way up. Now, remember, I'm not including 0. It's never going to have a point on 0. Okay, number last, we're almost there. I know y'all are probably way, way done, but we're almost there, I promise. Okay, the graph represents bacterial population after population Y after X days. So I think I'm going to make a table just to kind of look at what my values are doing. X, Y. So at 0, I'm at 3. 1, I'm at 15. 2, 75. That's growing fast. 3, 375. And 4, 1,875. So if we look at what's happening, we know it's growing exponentially because I can see the graph. So I'm multiplying or dividing. Well, in this case, I'm multiplying by 5. So it's growing really fast. So this is my B, my common ratio is 5. And it also gives me my A, whoops, right here. So if I were to write an equation, which they want us to do, I've got the equation is written y equals, again, A times B to the X. Well, figure out how to write this better. I'll do it underneath it. Okay, y equals A is 3 times B, we said was 5 to the X. So there's our equation. It says identify and interpret the y-intercept. Well, the y-intercept is this. It crosses at 0, 3. So there's that. And so based on this, we're talking about bacterial population after X days. So if we have 0 days, I started with 3 bacteria. Sorry. So on day 0, before I started this, I had 3 bacteria. The domain and the range. Well, in this case, since it is an actual real-life scenario, the domain is 0 because I can't have negative days. I can't go to negative infinity. I start with 0 and I work my way up. So in this case, domain is 0, and I'm including 0 because I can have 0 days. That's right here. 0 days, I have 3 bacteria. But then I can go to infinitely many days. We don't know if she's doing it for 10, 100, 500. So it goes from 0 to infinity. The range is going to be, it's never going to cross that x-axis. So 0 all the way to infinity. And we're not including 0 because remember that's an asymptote. So that range is the same as all the other ones we've been doing. But just because it's a real life scenario, we have to think sometimes there can't be negatives and days cannot be negative. They can only be positive. It wants to know what's the population after 5 days. So I'm using my y equals 3. That's my formula. Everywhere I see an x, though, now I'm plugging in 5. So now I've got y equals 3, 5 to the 5th. And when you plug that in your calculator, you get 5,625. So the population after just 5 days, we started with 3, and after 5 days, we're already here. Well, there's the intro to exponential functions. I hope you learned something. Y'all have a great rest of your day. Thanks for listening in. Bye.